We can start our record. Yes. And okay, we can share our presentation. Okay. So, I remind you that we have shared the notes on this part and on the thermodynamics. Okay. Okay. So, essentially, we considered the differential equation scheme for a steady flow like this. And today, in the morning, we have clarified our differential equation together with this 1, 2, 3, 4 boundary condition. In particular, the last two boundary conditions are related to wake properties which are translated by a primitive variable point of view into potential velocity potential point of view. Okay, and after this we have also linked this property with the boundary condition on the body. So clarifying this point, which is the Kutta condition relationship. And after this, we have introduced a very, very special solution, which is a solution for this kind of flow, but with no boundary condition, but just one very, very elementary boundary condition consisting of a point in the flow located at x star, where we are a symmetric constant spring of fluid, okay, with positive and with a mass flow equal to 1, okay. Mass flow equal to 1 means that if you take the flow of the velocity through any kind of closed surface around x star point, you have 1, okay. And so this flow is indicating the fact that we have a unitary spring in the point x star. The solution of this problem is the so-called source solution. And this is a possible contour plot of this kind of solution. Just let me do a point. The solution in terms of velocity potential in 3D is this here. In the case you have a 2D flow, this is 3D, you cannot imagine a 2D for this case as just a subdomain into 2D, because if you take the flow given by a concentrated source in a point, consider this distribution. If you take a plane containing this source, you see what happens in this plane. This is not correctly a 3D. A 3D should be not the field induced by a unitary source in a point, but a line of source. You have to consider a line of source in a straight line. And so you have a cylindrical field. In that case, that cylindrical field, when you take a plane cutting, you have the two-dimensional correct solution for a source. And for this reason, the two-dimensional source to be considered for solving two-dimensional problem is not this here, but is the following: Fg equal to the logarithm of x minus x star divided by 2 pi and not 4 pi. Okay, maybe there is a plus line, a plus sign here. Maybe there is a plus. Please check this. And this is similar to what happens in electrostatics, where you have a charge in a point, and you see the potential, the electric potential induced by charge. You have an expression, and this is a 3D case, elementary 3D case. When you have, if you want a 2D case, you have not to consider this case cutting, but you have to consider a line of charge per unit length, and then evaluate this cylindrical vector field induced by this potential, and then take the cut. And in electrostatic, you have an identical expression. One is like the logarithm, and the other one of type 1 on R. So you have the logarithm of R is the distance between the influencing point and the influenced point. Okay? This is just a bit clarification on the singularity. However, we have this solution. This solution is the solution G, which is the solution of this problem. So we have written the two problems, the analytical one with no boundary condition and the present problem to be solved. And we have multiplied by a cross product, and then we have taken the difference, and part of this difference can be recognized like a divergence of something. And so we have the opportunity here to apply the Gauss theorem. And we apply the Gauss theorem. And after the application of Gauss theorem, we have a unique integral on the closed surface. But this closed surface is very complicated. Is subdivided in subdomain, several subdomains. And the subdomain has infinite, the subdomain enveloping the body, and the subdomain enveloping the wake. But the time domain, the green curve here enveloping the wake can be taken to the limit, enveloping the wake, but the wake has zero thickness. The body has not zero thickness, the body is a body. And so your yellow surface here is actually exactly the surface in contact with the body. But this is not the case of the wake. You have a surface up and down, you can take this limit, and whenever you take this limit, you have a normal in the upper side and a normal in the lower side. These two normals are identical in direction, but the opposite in direction. And we will use this property for simplifying this unique integral subdivision, the red, the yellow, and the green, and we have concluded this, okay, today. Now, go ahead, and what we can do now? We can discuss the solution, and I want to be more, I want to go in detail on this expression. I want to correct this expression because because of didactical motivation, I have skipped a special particular to be considered here. When I have this equation, I would like to introduce here before applying the property of the Dirac delta function, I would like to include here a special function, the color violet. And this special function is E of x. It's a scalar function to be put here. This scalar function is a very stupid function. Note that this integral is on the volume, and this function is equal to 1 if x belongs to the fluid volume, and 0 if x belongs to the body. This is the body, black body, okay? Now, if you use this function, you can introduce this function here, and you can cancel and write R3, or the domain, or the fluid domain. Okay? This could appear as just a sophisticated and unessential maneuver, but it is important because the correct way for applying the property of the Dirac is to apply the Dirac property, but considering this integral as expanded to all the domain. Okay, so here correctly we can say this, and therefore we have here we have E x multiplying. This is also known as domain function. Domain function. Domain function. In the sense that when x belongs to a part of the domain, including the fluid volume, is 1. It's 0 if you have body. Okay. The set union operation between these two domains is R3. Okay, and so here we have E, and at the end of the story we have here E star multiplied x in x star. Okay? Because when apply the Dirac delta function property, I have to evaluate phi and the domain function, which are function of x for x equal to x star. And therefore I have phi evaluated in x star by E evaluated in x star. One could say, okay, I don't care, nothing's changed, but what is the point? The point is that if you go in deep and deep and deep, you can discover, and if I have time, I will demonstrate to you, that this domain function, which is equal to 1, what is it? Yeah, which is equal to 1 here for x in the fluid domain, and it equal to 0 here if x belongs to body. When you are in the intermediate position where body surface, the value of this function is 1/2 if the surface point is a regular point. Regular means the surface has a unique tangent. So to be more detailed, we have the following. We have that E is 1/2 if x belongs to S body. Okay. This is acceptable. You have a function, you have a space domain for in this zone the function value is 0. In this other zone is 1. In this point is 1/2. If you want to know the motivation of this, as I will show you later, I don't want to give all the detail at the beginning because I prefer to give you a general vision, then go back for the detail, the famous pilgrim step. 2 steps forward and 1 step backward. 2 steps forward and 1 step backward, and so on. This is the best for teaching. However, this value is related to the angle that an eye positioned in the x star point is able to view the body surface. When you see the body surface and you are out of the body surface, you are seeing with your eyes a closed surface. So the solid angle you are viewing the closed body of the surface is such that the domain function is 1. When you are inside the body, the surface is around you, and if you are an eye positioned there, the angle you see is the solid angle, is the radians equal to 4 pi. Remember? So, when you are with your eye inside, you have 4 pi. When you are outside and see the surface, you have 0, because the surface is 0, because you say the side of the moon and the dark side of the moon with opposite contribution. So the global vision of the closed surface is 0. But when you are on the surface of the moon and you see the moon, you see the surface of the moon, you see 1/2 of your solid angle. So you see 2 pi, not 4 pi, as the radiant source. And this is the motivation 1/2, because this domain function is related to the angle viewing. Okay? Okay, information, interesting information. However, let me go ahead now, and now we have at the moment this formula, this important formula here, and now I want to interpret this formula in computational and practical point of view. Interpretation. I have a couple of interpretations. First, for x star point of the fluid volume, you are here. For x star, you are here, and you have the following: E is equal to 1. In this case, E of x star is equal to 1, and so you have, I write phi in the point x star is equal to the integral on the body surface of d phi on the n, g minus, let me write explicitly the dependency of this variable, because they are important. So let me write the phi on the n, which is a function of x, by g, which is a function of x and x star, okay, minus dg on the n, which is a function of x and x star, and phi of x, function of x, ds, minus integral on the s wake, this is s wake, and this is s body, of delta phi, which is a function of x, dg on the n, which is a function of x and x star, ds. When you are integrating here, this surface integral is intended as integral in the x variable, not x star. So you have x here and x here. Okay? In the first case, you have a point here, and this formula is a representation of solution in x equal to x star if you know the solution on the body surface and on the wake. In fact, if you know the potential on the body, the velocity potential on the body, you know G, you know the G on the end, of course, and you know this, because this is the boundary condition. This is equal to body motion dot n. The body is moving. You know, imagine to know phi on the body. Imagine to know the delta phi jump on the wake. So you know everything in the right hand side. And so you are representing the solution in an external point. So this is a representation of the solution in all the points of the field. But you have to know the potential on the body. And so I can go to the second kind of interpretation of this formula, number 2. If x star is a point of the body surface, so imagine to take this point and put this point on the body. Here. In a fixed position. What happens to this equation? What happens is the following. In this case, you have just 1/2 here, because the domain function becomes equal to 1/2. But in this case, this equation is something like a compatibility equation to be satisfied by all the points on the body surface for having this flow. In fact, in this case, this equation is a compatibility equation to be satisfied by phi x, which is my solution, and another t-string point, phi x star. So note, phi x has to be integrated. Phi star is fixed. It's strange, but it's not so strange. Okay? So this is a compatibility condition to be satisfied by the entire distribution, all the distribution, a point of the distribution, this thing. Okay? And you can fix this point. You are able, you can to fix this point arbitrarily. And this is the point for organize a computational algorithm for determining your potential flow. This is the scope. This is the base concept for organizing a computational approach for solving the velocity potential on the body. So in this case, this equation becomes a compatibility equation to be satisfied by phi and phi x star. Okay? We will clarify this point, don't worry. And this is the interpretation, is very important. Another point, another interesting point, is this other aspect. This formula, another note, the integral equation can be also used for determining the velocity field V once you evaluate phi on the body. In fact, if you start by this, imagine to have an x star on the body surface. Then you have 1/2 phi star equal to blah blah blah, the phi on the end, g minus the g in the end, phi minus delta phi the g the end. If you consider an external point here, and you want to evaluate here the velocity in this x star point, consider, excuse me, in the volume fluid, not in S. I am, excuse me, this is not true for x belonging to the volume fluid here. Okay, so you don't have 1/2. If you take now the gradient of this quantity, but attention, I have to consider the gradient in the x star space. So the gradient star. Gradient star means take the partial derivative with respect to x star, take the partial derivative with respect to y star, and take the partial derivative with respect to zeta star in Cartesian coordinate. This is the gradient star. Okay. In other words, you have to imagine to have a double space. The physical space, the space, the coordinate space where you take the integral x, and another parallel space for evaluating your function. It is practically the same space, but you are separately evaluating your function. Imagine another domain, which is coincident, but it is another domain. Okay? And this doubling of the space was performed by G, because G is a function which is symmetrically dependent on x and x star. Depend on the distance between these 2 points, x star and x. Okay? If you take the star gradient of phi in x star, you obtain the star velocity, of course. And so in the left-hand side, you have v, right, in the x star point, okay, equal to integral in the b. Now attention, what happens when I apply the star gradient operator? The star gradient operator is not able to be applied to x dependent quantity, only by the x star dependent quantity, and therefore I can directly apply this, not here, but here. And this is analytic, remember, minus applied here, and this is analytic. Phi, which is a function of x, this is star, excuse me, star, function of x, ds minus integral on s wake of delta phi, absolutely not affected by the derivative, and then here we have again the gradient of the g on the n. And this is just to be explicit the fact that this value, once you know the boundary condition and the value of phi on the body surface and on the wake, if you know these three quantities, because you have evaluated phi on the body and you know the motion, you know the velocity in any point of your fluid domain. Okay, analytically. supposed to be known, supposed to be evaluated. Okay? Up to now, all this is very theoretical. I introduced this formulation. I have done a specific comment on this domain function, and I have obtained a couple of interpretations of this. This formula is able to represent the solution, is able to give a compatibility equation. And in the second meaning, using the second meaning, we are able to evaluate the velocity potential on the body. By using this second interpretation, we will define the algorithm for evaluating on the body the velocity potential and on the weight. And this is the scope of this last part. Today, I have introduced these three phases of the formulation of our problem: primitive variable, velocity potential, integral equation. For evaluating the velocity potential, we have to discretize the integral formulation, and the discretization of the integral formulation, the last step, is also known as boundary element method, BEM. So the step number 4 here is the space discretization of the integral, space discretization, also known as boundary element method. Question: do you prefer to discretize an integral or to discretize a differential equation in space? Discretize a differential equation means finite difference. You have a finite difference, you have derivative, and so you have to express the derivative as difference between quantity. And this is the standard discretization approach for differential equation. If you have a differential equation and you have to solve numerically, you have to use finite difference. And this is a kind of discretized approach. But now we have transformed the differential problem in an integral problem. So we have to discretize an integral. In the numerical point of view, it's better to discretize an integral or discretize a differential equation. What is better in the, for example, in the accuracy point of view? Do you have an idea? Also, remote people, do you have some preference?
In terms of computation, I think it's better integral.
Yeah. If you have a domain, and in this domain you have to discretize a differential equation by finite difference, and use a fixed discretization, fixed mesh, the accuracy, fixed mesh, the accuracy for solving an integral and the accuracy for solving a differential equation is higher for an integral. And this is one of the motivations for using, to prefer this boundary approach with respect to the original differential one. And this is the motivation of this fourth step here. This step, and this is the motivation of step 3 and 4. Reformulate the problem in an integral form and then discretize the integral. If you see the problem in a general point of view, we have inverted the Laplacian operator. The inverse of the derivative is an integral. And we have the original problem, which is a differential problem. And we have formally inverted the problem, writing the problem in an integral form. And now we are discretizing directly the solution. We don't have to invert any kind of matrix. Better, we have to invert the matrix, but this is not is quite different with respect to solve the finite difference and invert differential problem inverting a matrix. Okay? And this is just to discuss with you the fact that we have advantage in using integral formulation. And this is the advantage. Okay? So now we have to just to face our space discretization approach like this. Okay, and so we have the boundary element method, and this method consists of take your problem, take your body, imagine that the body is a wing, is an isolated wing, and imagine to have a wake. Ciao lezione. Ciao, ciao, ciao. Ciao. You have a wake. Please, a note. Wake geometry is, unfortunately, part of the problem solution. Okay, so I have a problem like this, and I want to space discretize the problem by a mesh like this. I want to subdivide the domain in panel. I'm subdividing the problem in panel like this. And also the wake in panel. I am trying to consider, as CFD people say, a structured mesh, not an unstructured mesh. It's a very easy, stupid mesh. For a CFD people, this is not a mesh. It's too stupid to be a mesh. Okay, I want to be stupid. And I am subdividing the body in M panel on the body, and N like Nepal panel on the wake. I know, I told you, we don't know the wake geometry. How can you subdivide? You don't know, please. Supposed to have, for a second. N panels. Okay? So I want to assume a zeroth order formulation. Zeroth order formulation means that all the unknown and known quantity, it is, are assumed constant in a panel, in the panel surface. What does it mean? Our zeroth order discretization means the following. You have a continuous curve like this. If you subdivide your domain in panel like this, zeroth order means that in this view, any quantity is considered to be constant in a panel like this, constant. This is zeroth order formulation. Okay? This is one division, 1, division of zeroth order formulation. Higher order, one order, second order, could be the grade of polynomial used inside the domain for approximating your solution. Zeroth order means constant value. Okay? This is, of course, similar to any other kind of discretization process like a finite element, for example. But this is not a finite element. We are not, please, we are not discretizing the fluid domain. We are actually discretizing only the boundary. That's the huger advantage, the hugest advantage of this kind of formulation. Okay, what time is it? 3 o'clock. We can stop and go with the discretization in the next hour. Okay? Question? No question.